Application to physics and engineering. Hydrostatic pressure and force. Fluid force is the force on an object submerged in a fluid. Laws that determine the pressure exerted by a fluid are follow. Fluid pressure P is proportional to the depth d measured from the water level. D is the distance from any point on the surface to the water level. Fluid pressure does not act in any specific direction. A fluid exerts pressures on each side of an object in the perpendicular direction. For example, take the top surface of an object whose distance from the water level is d. This is the depth of the object. The fluid mass, m, directly above the surface of area A is m equals rho times v, where rho is the fluid density, this is the mass per unit volume, and v is the volume of the fluid body directly above the surface. The weight of the fluid, which is already the unit of force, is defined to be the product of the mass and the gravity, mg. But the mass is rho times v, so the weight is rho gv, but the volume is the area times the depth d. And so the weight is rho gad. Pressure is defined to be the force per unit area, but the force is rho gad, and so the pressure is rho gad over A, which is rho gd. To summarize, the pressure P at depth d in a fluid of mass density rho or the weight density delta is P equals rho gd or delta d. The pressure acts at each point on an object in the direction perpendicular to the object's surface at that point only. What this means is that at any point on the object, the pressure acts perpendicular to the surface at that point on the object only. Since the pressure is rho gd equals delta d, rho g is delta. Rho g is in the SI system and delta is in the British or English system. We know that the SI system is used when meters or kilograms are in the problem. The British system is used when foot or pounds are used. The SI unit of pressure is the Pascal, PA, where 1 Pascal is 1 Newton per squared meter, or 1 kilogram per meters second squared. Pascal is small, so usually kilopascal is used. Mass density, the mass per unit volume, is denoted rho, the Greek letter. The factor rho g is the density by weight, where g is 9.8 meter per second squared, near the surface of the earth. The mass density of water is rho equals 1000 kg per cubic meters. And the weight density is delta equals 62.5 pound per cubic foot. Sometimes 62.4 pound per cubic foot is used. Observe that in the SI unit, the pressure is rho gd, but in the English units, the pressure is delta d. Delta is the weight density and rho is the mass density. The weight density is pound, which is already the unit of force. Thus the force is rho gad in the SI unit or delta ad in the English unit. We know that the SI unit is used when the units are in meters or kilogram, and the British units are used when the units are in foot or pound. For example, calculate the fluid force on the top, bottom, and the side of the box of dimension 2 by 2 by 5 meters, submerged in a pool of water with the top 3 meters below the water surface. The density of water is 1000 kg per cubic meters. This is the SI units because meters is the units of the dimension. This box is submerged in water 3 meters below the water surface. We're looking for the fluid force on the top, the bottom, and each side of the box. Since the SI unit is used, the force is therefore rho GAD. Keep in mind that the force is the pressure times the area. The higher the pressure, the higher the force. The deeper we are from the water surface, the more pressure we'll feel. Consider the top of this box. Any point at the top of the box has the same depth from the water surface. The force is the pressure times the area, but the pressure is constant at the top of the box. And so the force is rho GAD. Rho is the water density, 1000 kilogram per cubic meters. G is the gravity, 9.8 meter per second squared. The area is the area of the surface, which is 2 by 2. The depth is 3 meters from the water surface. This is 117,600 kilogram times meter per second squared, or 117,600 newtons. Similarly, any point at the bottom of the box has the same depth from the water surface, so the pressure at the bottom is constant. The force is rho GAD, 1000 times 9.8 times the area, which is still 2 by 2, but the depth is now 8 meters from the water surface. This is 313,600 newtons. Observe that even though the area of the top and the bottoms are the same, the pressure at the bottom is much higher than at the top. For the side of the box, the pressure is not constant because points on the sides do not have the same depth from the surface water. With any case in calculus, we're going to slice the side so that at any point on the slice, the depth from the water surface is constant. To do this, we slice the surface on the side horizontally, parallel to the water surface. To find the force on one side, we first find the force on the slice. This force is assumed to be constant because the delta y is thin enough so that at any point on this slice, the pressures are the same. The force on this slice is rho g ai di. Rho is 1000, the gravity is 9.8, the area of the slice is the length, which is 2, times the height delta y. For the depth of the slice, we position the coordinate axis so that the origin is at the water level. The distance from the water level to the slice is therefore yi, and so yi is the depth of the slice from the water surface. Thus the force on the slice is 1000 times 9.8 times the area to delta y, and the depth is yi. The total force on one side is the sum of all of the slices, assuming that we have n slices. Each of the slices has the force of 1000 times 9.8 times 2yi times delta y. But as n go to infinity or delta y go to 0, we obtain the definite integral 9800 times 2y times dy. We add up the slices from y equals 3 to y equals 8, so the limit of integration go from 3 to 8. Evaluate the definite integral, we will get 539,000 newtons.